Hello, everyone. Very warm welcome to the Net Zero Energy Building Knowledge Series. This is a platform for industry to share their expertise, knowledge, projects, products, even ideas to fuel discussions on energy efficiency and grow engagements for net zero energy buildings in India. I am Deepa. I'm an architect and a sustainability consultant at Environmental Design Solutions, and I'll be the session moderator today. This webinar series is executed under the MAITRI program supported by USAID. MAITRI is an acronym for Market Integration and Transformation for Energy Efficiency. MAITRI program supports three areas, which are energy efficiency in buildings, sustainable cooling, and training and consumer engagement. The program works in partnership with several organizations such as the Energy Efficiency Services Limited, Bureau of Energy Efficiency, and several others, as you can see here on the slide, to implement various initiatives. The market transformation approach includes creating business opportunities for the private sector, scale up of potential initiatives, enabling policies, as well as providing training for net zero energy buildings. MAITRI is supporting efforts moving towards a super efficient and net zero energy target for buildings in India. The NZEB portal is a one-stop site for information on NZEBs, and you may explore this further on our website www.nzeb.in. In our webinar today, we are going to discuss about climate-based approach to carbon neutral design. The title is indeed quite intriguing, isn't it? High performance goals such as net zero, near zero, carbon neutral, and others, they really require a certain mindset, approach, and a design process from the inception of a project. The process also needs to be high performance, just like the goals that they are aiming. At least from my experience, I know that this is easier said than done. And hence we need to see more successful examples to understand the implementation. Sorry. Throwing more light on this topic is our expert for the webinar, Pablo La Roche. He is the Associate Vice President and Sustainable Design Leader at Callison RTKL and a Professor of Architecture at California State Polytechnic University. Pablo has more than 25 years of experience in professional practice, designing and implementing sustainable low-carbon strategies in multiple projects of all sizes, as well as a lot of experience in research and teaching. He has published more than 130 papers on these topics in leading international conferences and technical journals. He has also authored the book Carbon Neutral Architecture Design in December 2011 with a second edition which has been published recently in 2017. And I've also had the privilege and the honor to be guided by him when I was doing my graduate thesis at USC. He joins us today from Los Angeles, and it's a bit late night for him. So I welcome you, Pablo, in this webinar. Thank you so much for taking the time and sharing your experiences with us. And I'll make you the presenter right now. And over to you.
Thank you, Deepa. Thank you very much for inviting me. And let's see. Can you see my screen now?
Yes, we can see this.
Okay, thank you. So let's just start a little bit of, as Deepa was saying, my background is really in architecture and sustainability, and I wear two hats. One is really research and teaching in a university. Right now I'm serving as interim director of the John Lyell Center for Regenerative Studies, in which we sort of do interdisciplinary research and topics that have to do with how to reduce our impact on climate change. And these topics range from buildings to agriculture. And then also working at an architecture firm, which is a global firm. We have offices in different parts of the world, about 1,500 people, and it's very, very exciting work developing high performance projects in different locations. So just want to start quickly with what is carbon neutral with and there's many definitions, but one thing that's important to understand is just if we don't know already is that to remember that buildings are responsible for 39% of the greenhouse gas emissions in our planet, product of the operations of these buildings and of the materials that are embodied in these buildings. So buildings are responsible for a large part of the greenhouse gas emissions that affect climate change. Now, how do these buildings emit the greenhouse gases? It's partly its operation, partly its construction. These are the two big things, but it's also disposing of the solid waste and also even providing and disposing of water to and from the building. In California, I don't remember the exact number right now. It's about 18 or 19% of the electricity used in California is actually used to pump water, the water that we use in our buildings, and the water that we drink. So when we're using water, we're also emitting greenhouse gases. So there's embodied carbon in the materials that we use for construction, the energy and water that we use, and waste, we're always going to be producing it. So the first step is really to reduce all of these sources of emissions, right? We have to reduce emissions from energy, water, waste, and materials. And then the next step is really add renewable energy to offset the remaining emissions. So we're going to look at it as, a simple math. We're going to see that the sum of all of these emissions have to be offset by renewable emissions in green, just as simple as that. Now, so a truly carbon neutral building is going to be carbon neutral in all of those sources. Now, when we talk about net zero carbon buildings, these are buildings that are highly energy efficient and fully powered from on-site and off-site renewable energy sources. So we make these buildings very efficient, and then we offset whatever emissions we still have left with renewable energy. And this number has to be equal to zero on an annual basis. So what we're talking about is really this first part of the equation, the operations emissions offset by renewable emissions. So this might be about 70, 75, it may be 80% of the emissions from a building are coming from the operation of the building itself. And how do we do this? Um, this is where we come to what Deepa was talking about. It's net zero energy buildings. A net zero energy building, by definition, is also net zero carbon for operation. So and how do we achieve this process? We increase efficiency of a building, we implement passive strategies, and we implement renewables. So we have to do it thinking in this way, in this process. We have to make it very efficient. We have to make it perform well. We have to think about climate. We have to think about the strategies that we can do that are appropriate for that location. And then we implement renewables, which right now we're talking about renewables on site or off site, but we need that clean energy to offset whatever energy we're still using in the building. So again, increase efficiency, passive strategies. I always say understanding the shade, understanding the sun, understanding air movement. Just simple things that I'm sure everybody sort of understands is solar geometry, air movement. Just understanding these two things take us in a well to what we need to do to respond to nature. Daylight is also important. It's not only more energy efficient, it satisfies biological and psychological needs that become apparent with more and more research. It's just very important for our wellness overall. And as a shade as a measure of solar control. And there's many different ways to design shade that can be, we could do like a whole presentation on how to design shade and basic principles of that. Renewables and then renewables at the end. So I would say that climate responsive design is really the first step to carbon neutral. And that's something that I want to emphasize with a couple of projects that I want to talk about. And we have to understand that we cannot do buildings the same way, and we're in different parts of the world. There are different climates. If we look at the ASHRAE climate zones, we're going to see that we have all of these different climate zones, and our buildings should feel and work and perform differently in these different locations. These can be roughly divided, sometimes just to make it simple. And I think about hot and humid, hot and dry, temperate and cold climates. It's a good way to sort of think about how the building will connect with outdoor climate to make, let's say, to achieve two important things in the building: reduce energy consumption and still maintain comfort. And the building will then respond differently depending on the climate, depending on the location. In a hot and humid climate, we want to maximize natural ventilation. In a hot and dry climate, we might want evaporative cooling. In a cold climate, we want to be more compact while still providing some passive heating. So again, we have different types of solutions depending on the climate. Now, I always feel that to achieve this responsive low carbon architecture, we must advance three things: education, research, and practice. We cannot just do one of them, and I think people do things in either one. I think that's great. So it's really important to um, push or let's say push all of these different areas. And I'm just going to talk just very briefly. We could talk again, like for each one of these hours, but I'm just going to talk just a little bit about education and about education in the United States. Uh, I think a simple problem is that not everybody is exposed to the level of depth that is needed in sustainable design when you're studying architecture. Everybody has a basic level that is maybe 2 semesters worth of sustainability, but they're only introduced to more advanced concepts such as energy modeling, right, which is an important tool, or the design of zero net energy buildings when they take advanced grad studios or undergrad seminars or upper division studios, because these classes are simply not a requirement. So only a small fraction of architecture students can enroll in them. So there's all sorts of different things that we need to do with education, like pushing sustainability early on, making more design applications and that have to do with sustainability in the studios. But I'll just mention one that I think is important, which is learn by doing, which is something I think we do well in our university, which is really hands-on activities that provide students with unique learning opportunities. It really is about, I really believe that students, and I think it's something that I learned when I did my PhD, is really the principle of designing, building, and testing. So really, when really testing and exploring that ideas that students have and that you will have later on as an architect, um, to test them. And this testing can be physical, right? Can be through models, through physical models, but it could also be through building simulations. But again, it's learning by doing. And I wanted to show like an example of a community center done in Mexico that was designed in class in a studio that I did. We worked with the community in Mexico, and we worked with a nonprofit organization in the United States, and students design or worked in teams to design different proposals. We went to Mexico, we talked with the community. This was very close to the border of the United States, uh, in a town called Tecate. And then students started testing some of the ideas that were implemented in the project. And this was done over several classes, over several years. But again, this idea of testing some of the ideas, I'm doing some research, and then building it with the community and volunteers. And then you can see some of the ideas here on the left, on the upper left, there's a solar attic for the winter and an evaporative cooling tower, which were actually ideas developed by these are concepts that already existed, they didn't invent them, but they were tested by the students also, just to learn also how they worked. And then these are students working, building the evaporative cool tower, and the center could be built in phases. And again, it's very simple. And in the summer, we have the evaporative cooling that provides cooling from the tower, from the chimney, and then it goes out through through the solar attic. And then in the winter, this upper space is heated. We call it the solar attic in the winter. We have a fan that pushes it down and then provides some hot air from below, sort of like a displacement ventilation system. And this is still the center is working right now, and it provides learning opportunities, daycare center for the community. It's a place for the community to connect. Research, I think is important also to push further advance the profession. Just a little bit on the green roof research. This is a Cal Poly Pomona testing different types of green roofs. In this case, for example, is one that does radiant cooling. There's water that moves through the soil. And I think I don't have the image here for that, but it's the water is cooled by the irrigation at the grass, at the plants, and then that cool water moves down below and absorbs the energy from the space underneath. So in a way, the soil, the green roof is working as a little air conditioner that absorbs the energy from the space, moves it through the soil, is transferred heat to the soil, and then by misting, does evaporative cooling up over here and is transferred to the atmosphere. This was developed in Cal Poly Pomona, and then we tested it in practice in something that we called the xylem, which is really an outdoor element in which we have some of the same principles. Again, we're testing the principles in research, and then we're implementing in practice. And you can see that it doesn't have to look the same way, right? We're testing them in boxes, but then we're designing a form that can be more interesting, in this case, to maximize radiant cooling for the person underneath, and trying to maximize outdoor comfort by doing more than shade in a hot climate. By doing a little bit of radiant cooling, you have the air movement, and then you're cooling these coils of water with the earth on top. We did different types of, and again, this is sort of like the simulations to see how the wind would pass underneath. And we really think that these could also have a reduction, an effect on the heat island, to reduce the heat island effect. So they're not only helpful to provide comfort for the person underneath, but they're also helpful to, when we have many of them, to reduce the heat island effect. So again, just ideas that can be tested in research and then implemented in practice. So then in practice, I think the big idea here is really to go towards a model that is more regenerative than just sustainable, something that can help, uh, let's say, improve the environments around the buildings, creating a better environment that is initially found. And how we do this in practice, how do we work in the office? These are all sketches that I do for projects, for different types of projects, and it's really meeting with design teams to propose ideas that are based on the ideas from the teams, but we want to make them better through sustainability. We want to make them stronger through sustainability. We analyze these ideas. And then in a sense, we're looking at priorities, we're proposing ideas, we're analyzing them, we're discussing them. We might go back and analyzing them again, and then we develop them further. But it's sort of this interactive or process in which we have different iterations in which we're working to develop and test ideas. So just as I said in the education in the university, in practice, again, it's all about creating, designing, proposing ideas, and then testing them, validating them in some way to see if they work. And we do different things during the design process. When we're talking about energy, when we're talking about light, when we're talking about the envelope, we're talking about the side. So we do, of course, our climate analysis, we do shade studies, we do solar studies, we do daylight studies. This is just to sort of looking at the phases in the design process conceptual design, schematic design, design development, construction administration, different things that could be done. And we don't do all of this in every project. It's in one project we might do, for example, just daylight. We might just be working in the skylight design for an atrium. In other projects, we might do a lot more comprehensive work. But again, just to give an idea of the different types of things that we do. So we've been talking about climate, and then one of my big passions is really passive cooling. You know, how to really make our buildings perform as the air conditioner. And what is really interesting about passive cooling is that uh, we are we're designing a building that is actually cooling, uh, lowering the temperature of the indoor environment through passive strategies by moving energy from the building to a heat sink that could be outer space, water, the air, or even the soil or the ground underneath. So again, it's just this idea of the building as an air conditioner, or we're talking about passive heating, the building as a furnace, but again, it's the building itself that is working through it. So if there's some of this work is, as Deepa was saying, is collected in my book in carbon neutral architectural design, and there's another book in which there's a collection of essays, in which there's also some work from different authors that is also touching some of these topics. But in this presentation, I'm just going to talk about a couple of them. I have examples for cooling with air, cooling with water, and cooling with sky. But just because of time, I'm just going to talk a little bit about cooling with air and about shading, which I think are the most important ones for this type of climate. So the first step when we're going to talk about passive cooling is really providing shade. And it's important to understand that when we're providing shade, we're not really cooling a building. We're just keeping it from overheating. We're just blocking the solar radiation that would otherwise overheat that building. So it's sort of like a prerequisite to provide passive cooling. So I'm going to show you an example. This is an airport that we're working on. This is in Guadalajara in Mexico. And it's a terminal. We're working on Terminal 2 of the airport. And apologize that I didn't have time to translate it from Spanish, but just to give you an idea of the process, we start with a very detailed climate analysis. Again, like I could talk for a long time of just about the climate analysis for this project. Based on that, we propose some ideas that have to do, it's sort of what we also sometimes call bioclimatic design. We're in constant interaction with the design team, let's say the team that is actually designing the project. We do solar studies, and I'll show you an example of that to how to provide shade, how to see if the shade is working. We adjust the envelope based on these studies. We do daylight studies, we do glare studies, and then we do like an energy study. So in this project we haven't done energy yet, and I think this is going to be done with this project with an engineering firm, but we've done a little bit of all of this already. And as we work with this process, we're talking with the architect, with the design team, and with the mechanical systems team. And one of the first things I really want to emphasize is that, again, is understanding climate and how energy interacts, let's say, how the building interacts with climate through three types of heat flows: radiation, infiltration, and conduction. In this, and I'll show you this images in a little bit, but just think about this. This project it's relatively hot, and we want to have transparency. So how do we provide that transparency in a hot climate? We shade it. So we want to be sure that it's shaded. We block heat flow also by conduction. We don't want this to get very hot on the inside. And we also provide a cool roof to provide some emissive heat loss from the roof itself. And then there is some potential actually looking at climate for about 4 months of the year from a little bit of evaporative cooling of the outdoor air around the building. So if we understand how the climate is and how the building should respond to that climate, we can do a couple of things. So like I said, this is just a couple of the images. We looked at the temperature. This is showing the whole year. and we're looking at temperatures that are above 20 degrees Celsius, showing us that we need some shade over here. And then also when we're looking at solar radiation, so we find that the time of the year in which we have highest solar radiation is from March to July. So we know, for example, then that this time we're going to have the highest temperatures and the highest solar radiation. It's even more critical. So we actually did solar studies just for this critical period, just for from March to at the end of July, just to see how the building would behave during that time. And we also did some annual periods. Again, all of this based on understanding of climate. I had this, so here it is, the same diagram. And just to show you how we do some of the studies, for example, if we're going to do, one of the first things that we did is, this is all, we want transparency here. If people are waiting for their planes to depart, you typically want to sit close to the plane and you want to see your plane, you want to see outside. So we wanted to provide some transparency. And but then this was west facing, so we started by providing an overhang, and it's a large overhang that actually looks really well. It works really well with the project. So if we compare like the solar gains on that glass wall without any type of protection, we're getting about 100 kilowatt hours per square meter every year. Just adding the overhang, we're down to an average of about 400, about half of that, 385. And then we also looked at the interior, the solar radiation on the interior, because we also wanted to control glare. And you're going to see this. This is frit, which is like a texture, like a sketching, a silk screen on the glass. And then that is actually also helping us to control glare. For example, this view, this is a glare analysis. What you see at the upper right is a person sitting, looking outside. And this is showing us in green, you see the 12 months of the year and the 24 hours of the day. More red means that there's more glare, and you can see that more glare is around 5 p.m. in the afternoon, right? When the sun is setting on the west side. Just adding the overhang cuts the glare by about 60%, and then adding the frit almost reduces the glare to almost nothing, except when the sun is really low in the sky. So again, we can use these tools to sort of understand how to provide transparency while still controlling glare and daylight and heat. We did a whole series of studies of the envelope. And so this is just one of them in which we're looking at problem area. For example, we found that this facade over here, which is facing sort of the southeast, is not sufficiently shaded by this overhang. So then we add, the design teams add more shade at that lower area. So again, it's sort of this interactive process between testing something and proposing a solution to that problem. And then we can provide some transparency. We can provide views, we can provide daylight. Well, also, right, we're also blocking the direct heat. We're testing that, as you've seen over here, right? So this area is shaded, but not that area. And so again, just some views to show you a little bit of that. The final project I want to show is a smaller project. This is in just to share a little bit of how to integrate these projects. It's a residential project. I did this actually before joining this firm. We did it, 3 architects. I did it with Mustieles and Oteiza, and it was product of a competition in the Canary Islands. And the project is net zero energy. And I'll show you a little bit of sort of the thought that went for that project. Like I said, it's Canary Islands, and we have the Atlantic Ocean to the south, the Tato volcano to the north. And we decided to organize the building based on solar geometry, which is this east-west orientation, and the winds, which would be coming mostly from the northeast. So the second floor, actually the first floor is connected with the wind. The second floor is connected with solar geometry, and the rooftop, we have a wind scoop that is actually connected with the wind also to capture the wind from the northeast. So this form that we have that you're seeing in ground is sort of responding to this basic sort of, again, climate guidelines, right? It's the sun, it's the east-west orientation. We can shade easier to the south. We're protecting psychologically and also in reality from the sun that is coming on the north side. Well, in the summer, we're getting some summer sun in the afternoon and in the morning, and we're capturing some of the wind also through the wind scoop. So when we look at the psychrometric chart, we're seeing that the climate is really nice. It's actually really close to the comfort zone most of the year. So we did some little bit of building simulation, and it works really simple. It's basically open in the summer, day and night for the winds. So as possible, we have natural ventilation, and then some shade during the daytime as needed on the south side. And that's all it is. And of course, insulation and other sort of materials but as a concept, that's what it is. And then in the building in the winter, it's closing. The building is enclosed to ventilation, but it captures the south sun for heating. Now the building does not have any heating and cooling system, which makes sense. It's a mild climate, but there's many of the new buildings over there do actually have mechanical heating and cooling. So this as a section, we have it so that it captures the wind. And what you see here is the second story, the balcony, and this is underneath the wind scoop. So we're actually living and using the wind scoop. So the wind scoop is underneath the space, and it's a usable space. This is one of the things that we wanted to do also. We want to integrate the systems that make it sustainable with the architecture. The south facade captures the sun. Daylight is abundant daylight. And this is located at the ITER, Instituto Tecnológico de Energías Renovables, like I said, in the Canary Islands. And they've been monitoring the house over several years. And it's really interesting to see inside the house. It's pretty much in the comfort zone all of the year, except a little bit here, which is in the comfort zone with air movement. So it's comfortable year round, and then of course it's also comfortable outside year round, but it responds pretty well to these outside forces, which is really something nice. And the house is rented, and it's comfortable more than 90% of the year. It's achieving thermal comfort with passive bioclimatic measures, air movement and shade in the summer, and solar gain in the winter. And as you can see it, and the building also generates more energy that it uses on an annual basis. These windmills are actually used by the institute where it's located to generate energy, not for this house, but they actually sell this energy to the community. And they're not so close to the project. This can be rented, and it's what we've heard is that people are very satisfied with it as a rental. So finally, then, what should we do? I think a couple of things I think are important, and embrace technology. I think is important when it improves design. So whenever we can embrace technology to improve the performance of a project, I think we should do it. Understand basic concepts for creative problem solving. I didn't talk much about this, but I think it's important to understand principles, to go beyond checklist, to really, if we want to do innovation, if we want to innovate, we really have to understand how things are working, to go deeper, and then develop something out of those concepts. So I think that is really in my teaching. I didn't mention that, but I did talk a little bit about conduction, convection, radiation. It's really understanding these basic concepts that makes you understand how buildings perform in different climates. Embrace simple. I mean, that is usually better. Just simple solutions, right? We can embrace technology when it helps, but otherwise, let's just keep it simple. And that is something that that I embrace as much as possible. And then think passive, using the building. Um, sorry, this, sorry, this animation. Okay. Uh, and then finally, I would say, we should go, where should we go with all this? We had vernacular buildings uh, that were and still are very admirable. I really love vernacular architecture. I think we can learn a lot from it because these were buildings that were designed by non-architects to respond to local climate and local culture in an effective way. Then there was a period of techno architecture, right? Sort of like, let's put all of these systems as much as we can, just to make our building perform better. And it's complicated. Something breaks, we don't know what to do. Nobody understands how the building operates. It's too hot, it's too cold, it spends a lot of energy. But I think now we can do more like a climate responsive building. Again, sort of combining learning from the past, learning how buildings have been integrated with the climate, but using the materials and the technology that we now have to have them perform and work well in these times. Thank you. So I think we're ready for questions.
Yes, thank you so much, Pablo. Those were like great, interesting examples. And we are already having some questions coming in. I thought I just had one question from my end to you because I'm
Mhm.
curious. You're an architect, and you are also a sustainable design leader at CallisonRTKL, which is an architecture firm. So what exactly does your everyday work look like? Do you talk to, the architects all the time, or do they always come to you for recommendations? How does that process really work? Or do you have like a big team so they can talk to everyone? How does that really work?
Yeah, that's a good question. So I can tell you, for example, today, right? So I think let's say just about today, and I'll tell you, how my day has been. So well, I don't know. I'm just thinking, wake up, connect with our office in London in the morning, like at we talked at 7:30. Last night I had sent them work. We're working on a project.
Okay.
I sent them work. We discussed it this morning. Actually, we had a short meeting with the client. We let's say what I like about working in projects such as that one is, for example, let's say the designer in London, we have
Mm.
has an idea. Okay, so let's say, and I wish I could show that, but it's sort of like a sketch to do something. And then where he's asking me, well, what do you think? Will this work for this climate? Or, is this, it's an office space. Will this provide daylight? I said, well, no, it doesn't, but then we can do this. So then another idea comes out of my side, and then
Right.
and that idea is sent to them, and they make it even better. They make it better. So it's like I I started building from an idea that they had, which is, let's say, just something about a skylight, but that idea sort of generated something in the whole project that came out to be really interesting, but it's working like back and forth. Then and I think that is like other project in the afternoon was a local project here in LA, but we have a small team. We do really what we try to do is sort of this sort of generation of ideas and testing them. We have
Mm.
software for let's say daylight. So we're testing if this skylight works better than that option, or we need that skylight or not. We test it. I always say, well, I think this could be happening, but let's test it. So we have everything in either in working with Rhino, Sapphire, or SketchUp with Sapphire or Diva or whatever program we need to to get the task done. But
Mm.
it's really sort of generating these ideas and testing them, and working with teams as required. We also have a person in the group that does certifications, so we do lead certifications, well certifications. So we do all of that also, which I think is also helpful. But it's even if the projects that are not certified, we do we try to improve the performance, and we keep track of the performance of all our projects. I didn't talk about that, but we report to
Mm.
20 architecture to AIA for 2030. EUI of our projects. We reported more than 400 projects this year, just
Okay.
to track our performance of the projects that we're working on.
Right, right. And do you also have this, do you train the architects in-house? Or is this is something they all understand, the whole technical information that goes into this work?
That's yeah, another really good question, because we do a lot of not a lot, we don't do as much as we should, but a training, like in-house training. So I think uh, the goal, and we're actually working right now, I think we're really well integrated. We have regular meetings with, like, let's say, design leadership,
Hmm.
design technology leadership, and sustainability and delivery. So we work together to try to see what are the best options to design our projects appropriately, design them sustainably, deliver them through, with Revit, with all the right, protocols. And then what are the tools that, so right now what we're doing is, so we're going to have like different levels of tools, like what are the basic things that everybody should be doing, right? Like
Hmm.
let's do like a solar study for a shade system for a building, or a climate analysis. I didn't talk
Hmm.
about really how we do, there's Climate Consultant, which I'm sure you're using,
Yeah,
and it's a free tool developed at UCLA, and it's everybody should know how to use that tool, and they
correct.
shouldn't have to come to me to ask me, hey, can you do a climate analysis of this location? Everybody should be able to do that. Everybody should be able to design, to know that if you're in a, let's say, at 35 degrees north, like in LA, you're not going to put a vertical fin on the south side, right? Simple things like this.
Hmm.
So I think we're really pushing for this basic level of knowledge that starts in school and continues in practice for everybody. But it's I don't know. You're probably the same thing with you. It's a challenge. Everybody is busy with, like, as an architect. You have many different. They're pushing you and pulling you in many different directions. So
Yeah.
at the end, uh, a lot of times they call a specialist, which is my team. But what I really enjoy is like working together as a team to
Hmm.
develop a good solution.
Right. Thank you so much. Yeah, I think that's that push and pull is sort of there, and we need to navigate through that. We have a lot of questions from the audience, so I'll start taking them. First question from James. Uh, what is the greatest challenge to net zero buildings at the moment?
I think, well, let me, maybe the greatest challenge is that people believe that they're more difficult than they are. Maybe that's, it's, we can always, and this happens to all of us, right? We blame it on cost, we blame it on the client. We say, oh, the client doesn't want to do this.
Yeah.
It's too expensive. At the end of the day, it's our fault, including myself. When we don't do it, we cannot. I think we have to sort of take responsibility for this. And again,
Mm.
I'm including myself. I don't, I push as much as I can. I don't always win. It's but I think we have to take responsibility for doing the things that we need to do. And I think that responsibility is getting as close as possible to net zero. And we're doing also a lot of work now. Well, I say a lot, but not it's still not as much as we should on embodied carbon. You know, there's I think Architecture 2030 has really opened our understanding, and we're
Hmm.
measuring the amount of carbon that we have in our buildings that is embodied in the materials in our building. So I've talked just about climate and buildings, but we have to go even beyond that and talk about what are the materials that we're using in our buildings. And as you probably heard, you know, there's a lot of talk. We're doing a couple of mass timber projects in which we're measuring the amount of carbon that is sequestered inside the timber that we're using, and then
Okay.
we're designing them for this assembly. So we're designing them in a way that that timber can be reused in other buildings. So it just yeah, it gets I think it's the short answer is it's our responsibility to learn and to do as much as we can.
Right. Then the next question is from Radhika. Can you talk a little bit about thermal mass as a solution for climate responsive feature in architecture?
Yeah, yeah, absolutely. So I think thermal mass is appropriate in for example, in a hot and dry climate or in a cold climate in which there's sun. So thermal sun is definitely an advantage if you, for example, let's say in a hot and dry climate in which you can cool a building at night, right? You open your windows at night or you have a fan. Actually, my thesis was with thermal mass and not ventilation. My dissertation from a PhD is so you cool that thermal mass at night, and then during the daytime you close your building, and that thermal mass absorbs the heat that is being sort of absorbed by the building, is absorbed by the thermal mass and keeps the you know the space itself cool, as long as as there's enough thermal mass to absorb all of that energy. So in places in which there's a large temperature swing, thermal mass is really useful. In places in which temperature is very close between day and night, or in which there's not much use for thermal mass. In places in which it's cold and you have a lot of sun, like, you know, for example, Southwest United States, Arizona, New Mexico, in which we have, those are ideal places for thermal mass. I'm not sure in India, there probably is a climate like that, in which you have sun, in which you have uh, temperature swings between day and night. Well, sun in the winter. Well, I don't know if you have a much of a winter, but you do have your cold climate, right?
Yeah, we have
Uh,
a hot and dry climate zones here
yeah, yeah.
in
So
India.
in
Yeah.
that climate, in that hot and dry climate zone, definitely thermal mass would be helpful combined with night ventilation, as long as you combine it with night ventilation. So that's the, and I didn't talk about that also, but those little four little diagrams that I had were really responsive to those climate zones.
Right. Thank you. Then there is another question here from Girish. Please share your insights about regenerative design concepts like energy positive buildings in sustainability.
Yeah, I think regenerative design is where we should be going, right? It's the center where I've been teaching also is part of our college with architecture, and it's the Lyle Center for Regenerative Studies. It was created by a landscape architect 25 years ago, before people were really talking about that much even about sustainability. You know, he was talking about regenerative design. So I think what's important about regenerative design is really understanding, let's say, flows and outputs, inputs and outputs. Really, sort of looking at nature and seeing how nature does things, right? What comes out of a system in nature, how can we use that in another system, right? That is really, I think, the power of regenerative design. And then it's connecting with social issues, with biological issues, anthropology. I mean, it's at the end of the day, connecting all of these systems together, in which us people are just one of those components, right? We're not the center of the universe of all these systems. We're just one part of it. So I think
Right.
just understanding of these components as systems and inputs and outputs, I think, is really important.
Thank you. Next question is from Bhakti. Could you list some of the softwares as recommended for energy analysis?
Yeah, so we do, I think everybody has their preferred software. So, and we use also depending on even the platform that we're going to use. For example, if we get something in SketchUp and is very simple, we might use Sapphira, which I think gives us quick results, and it's a program that anybody could use. Uh, I think I would recommend it as a platform for um, as a general platform. I've used it in studios and I've used it actually in lecture classes with 100 students. And so we've used that. We used um, with Rhino, we use Diva for daylight and for solar studies. We use ISVE for airflow modeling. We use a Grasshopper for some of the climate studies, and we used, of course, Climate Consultant. What else? I'm probably forgetting things, but those are the ones that we use mostly.
Sure. Yeah, and there are so many of them, like you said, out there.
Yeah.
So there's a lot of options there. Okay, next question is from Dickon. How would you design? Thank you for the presentation regarding a rapid changing climate and future. How would you design with predictions and evidence-based simulation software for the future?
So you can do one of the things that and it's good. I guess the questions are good because they made you talk about things that you didn't mention, right? For all of these studies, one of the key things is uh, using the right weather file, right? So it's let's say when we do a simulation, let's say we're doing a project anywhere in the world, we first spend some time finding the right weather file. And a weather file is just a text file that is organized in a way in which it has at least 10, 15 years of data and gives us an idea of how that climate is. There's newer weather files now, like a second version that includes newer weather, newer climate, I think until like 2018. And there's other weather files that can be generated for, let's say, predictive weather files for, let's say, 2030, 2040, 2050. I'm not using those yet. I should. I think, but that's a simple way to let's say do predictive analysis, because all of your simulations are going to be based on that weather file that you're using for your calculations. I just want to stress the importance of what a weather file is, because if you might be 5 miles away from the weather file, but as you can imagine, their climate could be completely different, because maybe it's, one is in one side of the mountain and the other one is on the other side of the mountain. So that is something that's very important. Always spend some time finding the right weather file.
Right. So we have time for just a couple more questions, and the other ones we'll try to see how best we can accommodate. The next question is from Jian. When you start with any project, what data source do you consider for a base case, EPI or EUI?
Yeah, so it depends. Well, what we have is, for example, for 2030 reporting, we use CBEX, which is the Commercial Building Energy Survey, something like that, for 2003 as the reference case. Uh, if For energy, it could be whatever energy code we have for that location. Now, we don't do, this is something important, we don't do compliance energy modeling. So let's say the energy modeling that we do, I've mentioned daylighting, I've mentioned shading, I mentioned solar. We do a lot of work with the envelope. But for energy modeling, it's more like testing options. It's more like early phase modeling. So it's more like testing and comparing one option with another. For example, one massing or one glazing option versus another option. So it's more that type of thing than just that a full-fledged compliance model with all sorts of building systems in it.
Right. And one last question before we wrap up the session for today, from Priyanka. What are the important parameters to consider while selecting the materials to design a net zero building?
Well, I think the materials should be selected as intended for, let's say, for the required heat flow for that specific location and climate. And if we're talking about net zero energy, and I think how the heat is transferred through that material is extremely important. For example, the simple example is insulation, right? It's just insulation is typically used to block heat flow, right? To make our building uh, less exposed to exterior conditions. If you're in a very hot climate, you're keeping the heat outside. If you're in a very cold climate, you're keeping the heat inside the building. Now, so it's pretty simply, you would look at conductive materials or insulating materials. Now, I would go beyond that. For example, I didn't show one of my research project was a roof with an operable ceiling. So that ceiling would open and close depending on the heat, where you wanted the heat to go from. If you wanted the heat to escape the building or you wanted the heat to sort of come inside the building. And these are the sort of things that I always find a challenge to do. Like I cannot, or at least I don't know how to do building simulation, how to simulate these things with a program. So that is a big challenge. Like how do we, let's say we're actually making systems better than we can simulate them, right? So I don't know if I'm getting my point across, but it's like uh, materials for simulations might be just two things, right? Well, thermal capacity or density or insulation, right? All of these thermal properties of the materials. But I think it's important to understand also how you can operate these materials to adjust the heat flows between the inside and the outside. So how to make these operable, how to adjust these heat flows so they're not always static or one directional depending on the material.
Right.
I don't know. Yeah.
So,
Hopefully that
and
made
of
sense.
course, yeah. So I think that was our last question. There are some more, and I'd request the attendees to please, you can leave the questions on our LinkedIn page, and we could respond to it, and even Pablo could respond to it, and
Sure.
everybody gets the benefit to see the questions as well. Uh, and I just have a few things to share because we've come to the end of the session now. Uh, One second. Sorry, one second. Let me just go back to my slide. Yes. So before we end the session, just a couple quick announcements. I don't know why it looks like this. One second. Yeah. So the webinar recording for today's session will be available on our YouTube channel, NZIP India. Some of you have asked about it. So yes, please do check there. And we'll also have a write-up available on our website, and you could get a copy of the slides as well on our website to check back in a week or so. That would be available. And the next webinar in this month is on 27th on personal thermal comfort systems. This is research done by Professor Rajan Raval and the CARBS team from CEPT University. Very interesting work. So do sign up for the webinar. The link is also there in the chat box. So look forward to having you there in the next session. And with that, we end the session for today. Thank you so much for your interest and time. And do tune in for the next webinar as well. Thank you so much, Pablo, for your time and the wonderful examples that you've shared.
Thank you for inviting me. I hope it was helpful.
Yes,
Thank you.
absolutely. Yes.
Okay. Thank you.
Thank you so much.
Bye.
And you'll just bye. Yeah.